I'm on that.
But you need to know the difference between continuous and bright line. Big difference. All right. True or false? Bright line spectrums are unique for every single element.
True.
True. Did we write that?
Yeah.
All elements have their own unique spectrum. Good. Okay, that's it. That's all I want to do. Review those. Put that away.
Oh,
I wanted to review continuous spectrum, bright line spectrum, and now let's talk about how light is produced, whether it's from here, from a flashlight, from the sun, any light source, even little like the screen on a computer or a little tiny LED light, or like if you charge something that has a little light, lets you know the charge is on, little LED, any light source at all, they're all producing light the exact same way. And here's the way. We start with the ground state. So all atoms have a ground state electron configuration. The ground state electron configuration, actually I should add that, ground state electron configuration, so E-config. This is the lowest energy and most stable configuration. Lowest energy, again, on the ground here, right? We're on the ground, that's where we are most stable. If we jump up on top of a desk, we're not as stable. We cannot stay there. All right? Or if you're jumping up, hovering in the air, not quite as stable. On the ground is the most stable. So lowest energy, most stable configuration. This is the electron configuration on the periodic table, or maybe I should say in your periodic table, but periodic table. So if I was to ask Veronica, what is the ground state configuration for sodium, she would look it up and say 281. Whatever it is on your periodic table, in your reference table, whatever it shows, whatever it says, that's your ground state. That's as clear as I can be. All right, the whole lowest energy and stable, that's on you to remember. But as far as remembering what this is, as far as where to look it up, it's right there. So that you don't have to memorize that. It's right there. Okay. So that's the ground state. So all atoms, all elements, all atoms of elements have a ground state. Well, when you start heating things up or giving things electricity, and I say things, substances, elements, compounds, then this starts to change and they become excited. We're going to talk about that in a minute. Let's use calcium as an example. We'll just write this down so we have one as a point of reference. 2882, that's the ground state for calcium. That's the ground state for calcium. So, hope I'm being clear. If I say, what is the ground state configuration for zinc, what do you guys do?
Look at the periodic tables.
You just look on your periodic table and you read it off.
8, 18, type 2.
There you go. Okay, whatever it is, it is. That's the ground state.
I might mess it up, but it's okay.
That's okay. I mean, it's right there.
Yeah.
Right? Okay, you're not making it up. You just go look it up. Everybody good with that? We're clear on ground state. Because sometimes kids will get confused. They read a test question and they say something about ground state, and then they say to me, I've had kids tell me, well, that means lowest energy or stable, so do I have to start moving electrons down? No, no. It's already given to you in ground state. The only thing you have to do is the next part, excited, that's when you move them up. All right, so you're not moving anything down. All right, so that's ground state. Excited state. So the excited state electron configuration. So we got ground state, very stable, low energy. That's what's on your periodic table. But once you start giving atoms energy, heat, electricity, now electrons can become what is called excited. Why are we learning about this again? Don't say because it's on the test. Don't say because we're in chemistry. What did I say before we started taking notes? What am I trying to explain? Yeah, very good. Thank you. I was hoping at least one person had me there. Good. Yeah, how light's produced. Okay, you have to understand ground state, excited state to understand all forms of light. Light we can see, what's that called? Visible, and what's the light we can't see?
Invisible.
The rest of the electromagnetic spectrum, which is invisible to us. Yell out some other forms of light.
Infrared.
UV, infrared,
X-ray.
X-ray, microwaves, radio waves, gamma. Good. You guys hitting all the big
Cosmic.
ones. Cosmic. Good. Yeah. So we're gonna talk at the end of class. There's a video on the electromagnetic spectrum. It's a good video.
Radio
Short.
Radio waves as well.
Yes, radio waves. We're gonna watch that. It explains a little bit more about the whole spectrum, and that'll be it for the spectrum stuff in class at least. All right, excited state electron configuration. This is higher in energy, and unstable / temporary. Again, if I jump onto the desk or table or counter or bookshelf, whatever the heck, you want to jump up on something to symbolize, right? An example, this is me jumping up up to a higher energy level. I can't stay there. You couldn't either. You have to get back down and live your life. It's a pretty good analogy for why this is unstable and temporary. The electron's not going to stay excited. It's going to go back to the ground state, and usually it happens very quickly. I'll talk about that in a minute. Higher in energy, and I guess we could give this 2 stars, because this explains what this means. When an electron gains energy, underline gains energy, that is the key. That is the most important thing to remember. It has to gain energy first. When an electron gains energy, it will jump. I put that in quotes because obviously they're not jumping, they don't have legs, okay, but they're moving, but we say jump to help us visualize it. It will jump up to a higher energy level. Oops. Higher energy level. Actually, that's it. That's the excited state. That's how it works. You give an electron energy, it jumps up to a higher energy level, but it's only there for a little bit, and then it's going to come back down. I'm going to get to that in a minute. So what do we need to learn today? What is ground state? It's stable, low energy on the periodic table. What is excited state? High in energy, unstable, and how does it work? You have to give energy to an electron in the ground state, it jumps up to a higher level, now it's excited. So who can put calcium in the excited state?
2, 8, 8, 1, 1.
1, 1, very good, I'll take it. 2, 8, 8, 1, 1, good job. This one from here, jumped up, good. Will, you want another one?
Would 2, 8, 7, 3 work?
2, 8, 7, 3 would work, good job. Anybody have it? We'll do one more. Anybody want to throw one out there? These are good answers, good job. Because this one we're taking one from the third, bringing it to the fourth. I mean, that's good. We can just leave it at that. Well, what else could we do, though?
Can you move
2,
1?
7, 8, 3.
Yeah, you could do 2, 7, 8, 3, yep. Or 2, 7, 9, 2. There's a lot of different options. But to be honest, even in real life, these are the only 2 you're going to see. Like, this is the only 2. These are the most reasonable. As far as the whole attraction for the nucleus, the ones further away are the ones that tend to jump around. So these 2 definitely, probably. That doesn't really make sense. But these 2 really don't jump around a whole lot because of the pull of the nucleus, so it's usually the outside ones. So on regents, those are the 2 you would see. Which of the following is the correct configuration for a calcium in the excited state? One of these would be a choice, for sure. Yeah.
So potassium would be 2881.
Yes. In the ground state.
Yes. And excited state could be 28801, or can you
Could
not?
be.
It could.
Yep.
Okay.
Yep. Or 2872. Yep.
Okay.
Yep.
But you can't have an empty energy level technically.
Technically, you could. Yeah.
Okay.
Yep.
In real life?
Yeah. It can happen. Questions on excited state?
So excited.
Are you excited about learning this time?
No. Maybe.
Wrong answer.
Yes. I am very.
You guys seem to be fairly interested in whole color thing.
Well, it's because you like.
I like the lab better.
What do you mean colors thing?
Oh,
Color
sure.
doesn't exist.
Yeah.
That's really cool.
Yeah.
Yeah, the lab is cool. Yeah. Yeah, a lot of times talking about it isn't usually as fun as doing it, but everyone's different. What were you saying?
What do you mean color thing? Colors doesn't exist.
Yeah, colors don't exist, and that's well. Here we go. Now,
Great.
how light is produced,
God.
which gives us color. Without light, no color. Without light, no cell phones. Without light, no computers. Without light, no TVs. Without light, no communication except direct contact.
How about no life? Pretty much.
Yeah, okay, if we take it big picture, if the sun shut off, like all the light and energy stopped, obviously we can. Yeah. We could survive on Earth without artificial light. You know, at night we would just have to use candles and whatever. You know, but that is a form of light, so light's really important. So I think it's cool learning how it's produced, and no matter what form of light it is, whether we see it or we don't, it's all produced the same way. Basically. Here it is. When the excited electron, so we just excited it, it jumped up to a higher energy level. When that excited electron falls, put that in quotes, back down, where's it falling back down to?
Lower energy level.
Ground state or original, you can say original state, that's fine, that's good. Falls back to the ground state. Now let's make sure we really understand the concept. In order to jump up, you have to give it energy. So when it falls back, it has to lose that energy, right? Falls back to the ground state, losing energy, and really, if I was going to give very specific notes, I would say losing the same amount of energy it just gained, but that's kind of confusing to write it all, as long as you understand that. Whatever it gained, it's going to lose the exact same amount. So losing energy in the form of light. And that's cool to me. I think that's cool. That's how light is produced. And then what we learn, inside the light, but we can't see it, not with our eyes, inside the light is, okay, photons. Light's made of photons, but so white light, the light from here, the light from those gas tubes, there's more inside the light that we can't see with our eyes. So we use the spectroscopes. What does that do?
Wavelengths.
What are those things called?
Spectra.
Spectrums, right, spectra. And that's the toughest part for some kids to kind of buy into, that when this energy is released, when the electron falls, it's releasing spectrum. It's releasing a spectrum, but you can't see it unless you have a diffraction gradient, a spectroscope. So you need a prism, you know, something that can separate the light so we can see the different wavelengths. So yes, saying that light is formed this way, produced, that's great. I want you to remember that, learn that, understand it, but also remember inside that light, or maybe within the light is a better way to say it, or the light is made up of spectrum, which is plural for spectrum. That's all. Okay, and that's the colors, the rainbows, the bright lines, the different colors. And again, colors only exist because of the light and because we said so. We only name red because we named it red. Red isn't red on its own. It's just a wavelength with 700 nanometers. The color red and the name red is just because we decided to call it red. Just
Like
to be
any
clear.
word.
Just like any word, just like anything.
So how would every
I could be writing with a desk and this could be a marker.
so
I
how
could
are
be
the
named
different colors?
Susan.
You could be named Susie.
Yep.
Is it-
Okay.
So how about the different colors though?
Susie
So like
Sturman.
No, it's horrible.
You don't like that?
No.
Susie Crockett.
Alright.
Question.
What?
So with like different like what were different colors? Is there like
Different
more
colors or different wavelengths?
wavelength of red
So-
than there's blue then?
So so if I'm holding a rope, Alex is holding one end, I'm holding the other end,
Right.
and we stretch that rope out pretty far, and we start doing this, the peaks between them are going to be pretty far apart.
Right.
Would you agree? Can you visualize that? If we got closer and we did it very quickly, would the peaks be closer together?
Yeah.
Yes. The closer they are, the more violet. The further apart, the more red.
You should do that with a slinky.
Oh.
Mr. Decker did that. Now
Okay,
it's
I'll bring in a slinky and we can play with the slinky.
that.
Okay, good. Alright, so one thing I do want to mention though, about this whole energy thing, you don't have to write this, you've already done this in your notes, 2, 3, 4, 5, 6, 7. If you want to take an electron from the second level and bring it up to the 7th, I want you to really understand why it's got to gain energy. Each energy state has its own specific amount of energy, and there's a word for that. Starts with a Q.
Quantum.
Quanta. What's the most current model called?
Quantum.
Wave mechanical level.
Wave mechanical or quantum mechanical. The name is named after energy because each level has a specific amount of energy, like 100 joules, 200 joules, and that's not correct. But each level has a specific amount of energy, no more, no less. So if you have an electron with 700 joules, it cannot exist down here. It would have to lose 500 joules to get down here. If you want to live on the first floor, you need 100. You can't have any more, can't have any less. It's exact. That's what the word quantum means. It's a specific amount of energy. The analogy I use is money with hotels. $100, $200, $300 a night. Top floor, $700 a night. In real life, if you have $700, you can stay anywhere you want. So you can save money and stay in the 200. But in chemical terms here, with this configuration, it doesn't work that way. It has to be exactly that number or it can't exist. So when we wrote those definitions, that's why you got to give this one energy to get it up to 6, 7, 5, whatever, and then it's got to lose the exact same amount. Otherwise, it can't exist on that level. All right? And the funny thing about it is it works every time. Kids in the past have asked me, well, what if it only loses half the energy? It doesn't work that way. It's either, it's like, I don't know, if I drop the marker and I say, oh, I got to pick up the marker. And someone says, or I say I can't pick up the marker. And someone says, try. Like I'll say that to my daughter. She's like, oh, I can't do that. And I'll say, try. That's a foolish thing to say. Try and pick up the marker. What does that even mean? Either you pick it up or
There's
you
do
don't.
and do not. There is no try.
That's right, Yoda. I just bought my daughter a Yoda action figure for Christmas. She's into Star Wars right now, which is I'm amped up about it because she's been into like super girly things, which is not like high on my list of things to like be involved with. But now she's into Star Wars. I also got her. I got her. My wife's like, "Who did you get this for? Her or you?" And I'm like, her. It's a BB-8 like remote control thing. I can't
That's for you.
that. That's gonna be awesome. Anyways, she's gonna bug out. The point is, try, right? You can't try to pick something up. Either you pick it up or you don't. So the analogy there, sorry, I went off on a tangent a little bit, is the same. The energy is all or nothing. So in real life, when these things do this, they jump up, fall down. It's discrete quantities, so it always lands on a level. There's no, halfway or something like that. So I think I kind of beat that to death. If you only remember what we just talked about today and not the rest of the whole 3-4 minutes we had, that's fine. Ground state, what is it? Excited state, what is it? And then how is light produced? If you can remember those things, you're in good shape. All right. Now, last thing here is this video on the electromagnetic spectrum. We really don't have a lot of time.
Far enough away.
You can pack everything up. Yeah, we'll have to show it tomorrow.
That's not a good idea.